How does a country store enough fuel to survive a crisis, enough gas to survive a winter, and enough hydrogen to power its future? All in the same underground salt? The answer isn't a warehouse. It's dozens of hollow chambers, 2,500 feet tall, reached by pipes barely wider than a fist. Let's see what it actually takes to build an energy vault underground. Drive past a quiet industrial yard in Texas or Louisiana, and you would swear nothing important is happening. A few valves, a wellhead, some pipes. You would be wrong by about 2,500 vertical feet. Beneath that boring surface sits a hollow space, so tall it could swallow the Willis Tower with room to spare. Site selection depends on fresh water access, brine disposal routes, and the size and quality of the underlying salt. Seismic surveys map the deposit. Exploration wells confirm it. Then engineers design a cavern roughly 60 to 80 meters wide and 300 meters tall. From the outside, still invisible. And yes, the same vaults that hold America's oil also hold its natural gas. Compressor stations feed pipelines into steel tubes barely 10 centimeters wide. Those tubes drop through 500 to 2,000 meters of rock into caverns leached inside a completely impermeable salt layer. Summer fills them, winter empties them. The whole thing runs from a remote control room. Very quiet, ordinary, and utterly enormous. On the surface, America builds petrochemical plants stretching across 44 football fields with 40,000 tons of steel. That's the part everyone sees. Beneath the same coastline, enormous salt caverns quietly store the nation's energy reserves. To understand why salt became the preferred place to store energy, look at what's actually down there. The largest underground salt mine in the world sits under Lake Ontario at more than 1,800 feet below the surface. That's the height of the CN Tower buried point down. Miners walk into tunnels wider than a 4-lane highway and tall enough to hide a 5-story building. The salt was found by accident in 1866. A local mill owner drilled looking for oil. After 102 days, he hit a 40-foot layer of rock salt instead, which is how most great industries get started. Someone was looking for something else. Underground pathways run 55 feet tall to fit continuous miners the size of tour buses. 50-foot-long remote-controlled machines chew the walls in 4-pass cuts. 40-ton haulers dump broken salt onto conveyor belts. Beneath one small Canadian town sits a mine that stretches farther than the town itself does on the surface. How hidden is hidden? One European salt plant runs 140 kilometers of conveyor belts beneath the ground. That is 87 miles, underground, just to move raw salt from mining districts up to the surface plant. Nobody driving past has any idea. The same solution mining technique used to create America's underground energy caverns was first developed to extract salt. Water gets pumped 3 kilometers underground, dissolves the salt, and comes back up as brine. The surface facility is not the machine. It's just the handle. The real machine is thousands of feet below it. But before America can store energy and salt, engineers first have to build a steel doorway that cannot afford to leak. Every casing string protecting an underground storage cavern begins as molten steel poured into a vertical caster the size of a 20-story building, a $200 million machine. The largest vertical bloom caster in the world casts 4 glowing red bars simultaneously, straight down. Torches cut them mid-air, cranes flip them horizontal. All of that just to make the raw material for a pipe that will end up thousands of feet underground. Then the bar has to become hollow. Solid billets get heated to 2,200 degrees Fahrenheit in a rotary hearth furnace, then punched through the center by a piercing mill using a rotary process no three-axis machine could copy. The result is a seamless hollow ready to become oilfield casing. Wall thickness gets tuned per customer. Turning a hollow bloom into oilfield-grade casing is where boring becomes serious. Billets heat to 1,280 degrees Celsius, get pierced using the Mansman effect, and enter a stretch reducing mill that shrinks the outside diameter to spec. Then heat treatment. Austenitizing furnace above the transformation point, water quenching at high pressure down from around 900 degrees Celsius to make martensite, tempering to restore ductility. Straightening machines correct ovality within a hair. Every single pipe goes through hydrostatic testing, electromagnetic inspection, and ultrasonic wall thickness scanning. Because a pipe that fails 4,000 feet down is a pipe you cannot recall. Then comes threading, which is where close enough ends. Ends get externally upset by localized induction heating, so the wall thickens before machining. Couplings get threaded on CNC lathes. Every dimension is checked by hand with mechanical gauges before shipping. Every finished pipe still gets scanned again. Modular ultrasonic platforms. Phased array, EMAT, eddy current. Inspect weld zones, heat-affected zones, pipe ends, full body, and both surfaces at once. Ovality, wall thickness, laminations, edge defects. Because at pipe number 4,000, you still cannot afford one leaker. Now the pipe leaves the mill and meets the rig. Top drives sit fixed in the derrick, so rig up and rig down take less time. Technicians never touch the drive machinery directly. Safety by design, not by luck. But even the best top drive still needs 3 humans at ground level who know what they're doing. A drill rig connection isn't automated the way you'd assume. Roughnecks manage the moving drill string as each new section lifts into place, guiding thousands of pounds of steel with their hands and eyes. You misthread one joint at 4,000 feet down and the entire day is over. An iron roughneck, the mechanized clamp, grips the connection point. A chain wraps the upper joint and pulls it tight to spin the new pipe onto the string. The rotary table drives it home. Lubricants applied. Next joint stabbed. Watch it from the operator's chair and everything starts to make sense. One person works the hydraulics from the driller's console. Another swings power tongs on the floor below. The pipe rises, connects, locks, descends. Repeat 5,000 feet worth. Communication happens by gesture. Mistakes happen once. Before those hands are trusted with any of that, they were a rookie who didn't know what a tong was. Entry-level floor hands often work 21 days on and 7 off, 12-hour shifts, in weather most office workers wouldn't walk their dog in. Training happens on the floor. Older hands watch. Newer hands ask. The pay is real. The mistakes are unforgiving. Learn fast. The pipe is down. The seal is not. Cement slurry gets pumped through the casing and back up the annulus. Slurry weight has to sit in a razor-thin window. Too heavy and the formation cracks. Too light and formation pressure wins. A cavern the size of a skyscraper can be ruined by one bad seal at the shoe. Above ground, everything the cavern breathes through passes across a flange. The goal is zero leakage. Bolts get numbered 1 through however many. Hydraulic tensioners get placed on each in a synchronized ring. Hoses linked to a single pump so every bolt gets identical load. A single unloved bolt becomes a lifetime of, why is that gauge dropping? The tool doing the loading is deceptively simple. A puller screws onto the bolt threads, a cylinder rests over the bridge, hydraulic pressure stretches the bolt, then a Tommy bar tightens the nut against a now elongated shaft. Release pressure. Bolt stays stretched. The doorway is sealed. Now the excavation begins, and the tool that cuts the salt isn't metal, it's water. Now for the strange part. The tool that carves a cavern the size of a skyscraper out of solid rock isn't a drill, it's tap water. Leaching starts by lowering two concentric tubes down the sealed well. The space around the outer tube gets filled with an inert fluid, nitrogen or fuel oil, to sit on top and stop water from eating the roof. Fresh water pumps down the inner tube. Brine rises up the annular space. This is called direct leaching. Switch the flow and it becomes reverse leaching. Which mode you choose determines whether the walls widen faster or the ceiling holds sharper. Insoluble debris in the salt layer drops to the bottom as a sump. The pace, position, and switching of the tubes decide the final shape. Cylindrical body, vaulted top, narrow neck. Get the geometry right, and it can hold a monument. Get it wrong, and you carve a slow-motion collapse. Once leaching finishes, the cavern gets tested, then goes into service. Summer flows fill it under pressure through the same 10-centimeter steel tubes that leached it. Winter flows pull the gas back out, sending it through dehydration to strip water, quality checks in a lab, and remote flow control from a single room. 12 people. One cavern the size of a skyscraper. Every gallon of new cavern space equals a gallon of brine that had to leave. Tanker trucks queue up, hoses connect, field techs pull samples with dip rods, filter bags get swapped, the tank levels rise. Somewhere upstream, salt is being dissolved, and somewhere downstream, it's a full-time industry no one drives past on purpose. A cavern this big doesn't just create empty space. It also produces enormous volumes of concentrated brine. Depending on the site, that brine can become feedstock for salt, chemicals, pharmaceuticals, water treatment, and countless industrial processes. What looks like waste at the wellhead often becomes the raw material for another industry. Just one UDOT's rock salt mine supplies over 4 million tons a year for deicing across the Northeast. Stockpiles are combined and consolidated so that stormwater stays under control while capacity grows. Salt is not a waste stream, it's a business. Some caverns pay for themselves in brine. How do you compress natural gas or hydrogen into a storage cavern without exceeding the limits of temperature, pressure, and equipment? Before gas ever reaches the cavern, the well goes through every test engineers can throw at it. Two-phase testing runs, temperature logs, noise mics on the wireline, ultrasonic imaging of casing thickness, cement bond checks, magnetic flux leakage scans for pitting, multi-arm calipers for internal diameter, and hydrostatic pressure tests above maximum operating pressure. When integrity fails, someone has to fix it without pulling the whole thing apart. Wireline scans map the damage. Metal skin liners over 2,000 feet long get run in and expanded from bottom to top inside the parent casing. Corrosion, collar leaks, split casing, all restored without a workover from scratch. Now for the surface end. One recent US project replaced an 8,000 horsepower compressor station with a 32,000 horsepower monster, 4 times the muscle, built as 24 pre-assembled modules on 2 decks. Interconnect piping only, weather-independent build. The whole station arrived like Lego, enormous, expensive Lego. Inside those modules sits the real muscle, reciprocating gas compressors. Every time natural gas enters or leaves a storage cavern, these machines build pressure, regulate flow, and keep the entire system moving. Reliability is everything because a single shutdown can interrupt the movement of millions of cubic feet of gas. Long before installation, every compressor is precision machined, assembled, run tested under load, and signed off by inspectors whose names stay with the machine for the rest of its working life. Peel the casing off and the machine is almost embarrassingly simple. A crankshaft turns. A connecting rod pushes a crosshead. The crosshead drives a piston. Suction valve opens, gas fills the cylinder, discharge valve opens, gas exits at higher pressure. Repeat 300 times a minute. Not every storage site relies on pistons. When moving large volumes matters more than achieving very high compression ratios, engineers often choose turbo compressors instead. Single-stage and multi-stage centrifugal designs handle process gas at pressures up to 50 bars, while continuous monitoring systems stream live performance data to operators. Different machines, same job. Keep the gas moving safely. Speed a compressor station build up 100 times, and it looks like a perfectly organized ant colony. Red earth gets graded. Piles disappear into the ground. Cranes lower compressor modules onto prepared foundations. Pipe racks grow overhead. Control buildings appear almost overnight. Weeks of work collapse into a few seconds of footage. Only after all of this is finished can gas begin its journey toward the storage cavern. Behind every compressor sits a factory that treats each rotor like a Fabergé egg. CNC machined turbine wheels, robotic arm coating with high-velocity oxygen fuel, industrial impellers up to 1,800 millimeters across, welded and dimensionally verified with 3D metrology. Precision that expensive doesn't happen on the field. It arrives on a truck. Between the compressor discharge and the wellhead sit valves the size of small cars. Large bore ball valves get assembled body first. Cast steel shells, cleaned, measured, and fitted with seat rings and internal sealing components by hand. Chain hoists rotate the body between positions. Specialty welding reinforces internal structures where sealing depends on it. The bonnet drops in from above. Studs and nuts get pre-tightened, then finished with a hydraulic torque wrench that follows a numbered cross pattern. You look at one of these and realize why close the valve costs what it costs. Balls get polished to a mirror. Then the actuator lifts on. None of this stays leak-tight without the last person on site, the flange bolting technician. Approved torque specs get cross-checked against the field documentation. Low-profile hydraulic wrenches attached to the studs in numbered sequence. The pump cycles. Bolts stretch under load. A caliper checks spacing. A completion tag gets zip-tied to the flange when the job is done. No tag, no gas. That simple. Every compressor train needs a driver. Gas turbines draw in air, compress it, mix it with fuel, ignite the mixture, and convert that energy into shaft power. The same principle drives compressor stations across transmission pipelines and underground storage sites. The cavern sits out of sight below ground, but every decision controlling it happens above the surface, through turbines, compressors, valves, coolers, and pipework. A storage cavern can never be emptied completely. Part of the gas always remains underground to maintain the pressure the system depends on. Here's the strange part. When the cavern is full, operators cannot just empty it like a fuel tank. Storage caverns run on a cycle. Summer demand is low, so gas flows in. Pressure builds, inventory grows. Winter arrives, demand spikes, gas flows back out to the transmission grid. One 20 cavern project alone increases national storage capacity by 30%, holding roughly 1.5 billion standard cubic meters of working capacity. Working. That word carries a lot, because behind every working number sits another quantity that never leaves the cavern, and that's the one nobody advertises. Working gas is what gets pumped in and pulled back out. Cushion gas, sometimes called base gas, is the layer that never leaves. It sits at the bottom of the inventory, permanently, holding pressure so the working gas above it has somewhere to go. Multi-stage compression makes the whole cycle work. A 3-stage reciprocating unit picks up gas at around 30 psi and 80 degrees Fahrenheit. First stage, Compression takes it up to about 155 psi and 260 degrees Fahrenheit. An intercooler drops it back to 120 degrees Fahrenheit, and a scrubber pulls out liquids that condensed on the way. Second stage, pressure climbs to 490 psi, cooler again, scrubber again. Third stage, up to 1,200 psi at 240 degrees Fahrenheit, cooler one more time, and out the discharge at 120 degrees Fahrenheit. Suction control valves, recycle valves, scrubbers between every stage. Fail any one, and the machine either overheats or floods itself with liquid it wasn't designed to swallow. The working gas rides on top of cushion gas because physics won't let it any other way. And every one of those valves, ball, gate, choke, actuator, needs to be inspected, tested, and rebuilt on a schedule. Mobile service trucks, fully stocked repair shops, digital hydro testing up to 15,000 ACA, certified quality assurance packages digitally documented for every valve on every pipeline, because a stuck valve during withdrawal is not a small problem. Try finding a small leak by walking a compressor station with soapy water and good intentions. You'll be there all week. Acoustic imagers scan for the ultrasonic hiss a leaking flange makes and paint it on the screen as a colored blob you can't miss. Inspection speed goes up around 5x, roughly 30% of leaks that alarms miss due to air convection. The camera catches anyway. Large energy storage sites share more than one safety habit. Continuous monitoring, automatic shutoff systems, fire protection, secondary containment, and strict operating procedures all exist for the same reason, preventing small failures from becoming major incidents. Underground gas storage adds pressure management to that list. Hydrogen will raise the standard even further. Utah is where the future of American energy storage stops being theory. Renewable electricity feeds 220 MW of alkaline electrolyzers, splitting water into 100 tons of green hydrogen per day. The hydrogen goes into two massive salt caverns holding over 300 gigawatt hours of dispatchable clean energy. Nearby turbines burn it back into grid-scale power. First commercial operation targeted for 2025. Utah just quietly built the largest hydrogen storage facility on Earth. The mechanics are identical to natural gas storage, just with a different molecule going in. Fresh water dissolves salt. Brine gets pushed to surface ponds. Hydrogen fills the vacated space. The finished cavern reaches roughly 1,500 feet tall and 200 feet across. One cavern, 5,500 tons of hydrogen working capacity. Storage without delivery is an expensive hole in the ground. Every cavern needs pipeline. A modern long-haul steel line gets built as a moving assembly line. Right-of-way cleared 100 feet wide during construction. Permanent easement around 50 feet after. Trenches excavated. Steel pipe joints of 40 or 80 feet get bent to follow the ground contour without cracking the coating. Certified welders join sections into runs, several thousand feet long. Every weld inspected visually, then verified by radiographic or ultrasonic testing. Coating gets repaired at every joint before pipe drops in. Side boom tractors lower the string onto sandbag benches. Then the whole run gets hydrostatic pressure tested well above maximum operating pressure and held for hours. The pipe either passes or gets cut out and replaced. Nothing in between. Multiply that discipline by thousands of miles. And that's the invisible skeleton of American energy. Hydrogen makes every seal, valve, compressor, and material choice more demanding. Portable gas detectors are checked out through smart cabinets with verified calibration, battery status, and inspection records before anyone enters the site. No detector, no entry. Hydrogen is colorless, odorless, and leaks more easily than methane, so finding it quickly is part of the job. One quiet industrial yard. A few pipes. A wellhead you drive past without a glance. And beneath it, a salt cavern sealed with steel and cement, carved out by water over 3 years, mapped by sound, filled with fuel your entire country depends on. What looks ordinary on the surface can be supporting an energy system measured in billions of dollars below your feet. 60 caverns in the Strategic Petroleum Reserve alone, hundreds more storing natural gas across America, and now, 2 of them in Utah holding enough green hydrogen to reshape the grid. Ask yourself this: what's the largest structure you've ever stood on top of without knowing it? Share your answer in the comments. Appreciate you sticking with us all the way through. If you want to see more of how the heavy end of the world actually works, subscribe and see you in the next one. Take care.